All right, welcome to Lecture 10C entitled Double Integrals over General Regions. And in this particular case, we're looking at how we can apply symmetry when computing a double integral. This material is from section 16.2 of the text. However, it's not dealt with in any specific detail. The objectives are therefore to develop tools for solving problems involving symmetry, and the concepts or visualization skills are basically knowing how to exploit symmetry. Note this mathematical derivation is not in the textbook. You are not responsible for it, aside from knowing how symmetry can be exploited in order to simplify the calculation process. As usual, the second slide is just a summary of the contents to follow, so we'll just move on. All right, so exploiting symmetry in multivariable integration, we consider first of all the one variable case, which you're familiar with. So we start with basically the expression at the top where we have an integral between minus a and a. And so essentially the upper and lower integral essentially have the same numerical value, but one is the negative of the other. This is normally the way the problem is set up. All right, so we can then take this as a first step and split it into two separate integrals, one from minus a to 0 and the other from 0 to a. And then basically what we would do is just flip these two, and that can be done by just basically moving this to the top and the bottom, in which case we have to assign a negative sign here. So this is the first step, flipping direction of the integration here. The next step is to consider a change of variables for the first integral on the right-hand side, which is the one in blue. We let x equals minus x. In that event, this expression just becomes equal to this expression that you see here. And therefore, we can replace this expression by this to give an expression that looks like this. So effectively, what we end up with is a single integral from 0 to a, but the integrand now contains f of x and f of minus x dx. So now the question is, what is the relationship between f of x and f of minus x? Well, if the two are equal, then we say that we're dealing with an even function, and under those circumstances, the integral basically just twice integral from 0 to a, f of x dx. On the other hand, if f of x is minus f of minus x, this is equivalent to saying you have an odd function, then this integral becomes 0. Just for explanatory purposes, here is an example of an even function that is y equals x squared. Notice that basically you have a mirror image on the x side as well as the minus x side, whereas in the odd case, the value of y on the right is the negative of the value on the left. All right, so this is just a summary of the different cases that we'll consider in detail. So let's look at them one by one. Here I'm saying symmetry in x. Symmetry in x would mean either we're dealing with even function or an odd function with respect to the variable x. Here we're talking about even or odd with respect to y. In this case, we're looking at both x and y, either an even or an odd function. And the last one are conditional symmetries, where essentially we have two conditions, and then we want to see whether or not that has implications in terms of simplifying the integral. Notice here, for instance, that if it's odd, f of x of y is minus f minus x of y. So this was x, and so minus x and x appears. If it's even, then these two are equal. In this case, we're operating on y, so you can see this is y and this is minus y and minus y. In this case, we're talking about both x and y, and so you can see if this x becomes minus x, this y becomes minus y. So in one case it's minus, in this case it's positive, even functions when these two are equal to each other. So here all I've done is split it up by basically going through and indicating that we're going to basically break this up into two separate components from minus a to 0 and 0 to a, and this is the final result we get. The subsequent slides show you the details as to how this calculation is done. Similarly, in this case, you can see that we end up with minus b and b here becomes 0 and b here. And for the last case that you see here, you have two options, either from 0 to b or from 0 to a. Either one of these cases basically are equivalent to each other. Anyways, we'll show the derivation of these in the subsequent pages. Here are some conditional symmetries. For example, if f of xy equals f of x minus y, so this basically would indicate an even function, and f of xy equals f minus x and y, so this is an even function in x. Then putting these together is equivalent to also saying that f of xy equals f of minus x minus y. Under those circumstances, this double integral just becomes 4 times the integral from 0 to a and 0 to b of the double integral. Okay, so there's a very simple calculation to be done here. Rather than this calculation, this is much easier. An alternative would be, for instance, conditional statement 2, f of xy equals minus fx minus y, or f of xy equals minus f of minus xy. Under those conditions, basically, we end up with both cases, the integrals becoming equal to 0. All right, so let's look at each individual case in turn, symmetry in x. I'm not going to go through these in any detail. I think these are more or less, slides are more or less easy for you to follow through. I'll just point a couple things out. The first thing being that we split this now into 4 separate integrals. So there's always a 0 appearing somewhere in the integration bounds. And then the question becomes one of figuring out which of these integrals, basically, we're going to do a change of variables on, namely let x equals minus x, because we're dealing with the symmetry in x. And so this basically just shows the steps that are followed. And then the next step would be to substitute back. So effectively, this was equal to this, and now we substitute this back into the original equations, and then we end up with an expression that looks like this. The next step is to combine them. So finally, what you end up with an expression that looks like this. And this is something that was summarized in a previous table. By the way, these figures that we're looking at can all be accessed at this particular link if you wish. So you can click on that. All right, similarly, we will see for the other cases a derivation. Here we're just going to now look at what happens for the 2 specific cases, even x or odd x. And so in one case, if it's even, these two are equivalent to each other, so it's just twice times this integral. If they're equal and opposite in sign, it's an odd function, then this, of course, becomes 0. And so here's an example, for instance, where you have even in x, right? Y, of course, there's no symmetry. And here we have a case where it's odd in x. In this case, y has no symmetry, right? And so these are the results that you can conclude. All right, now let's try the case of symmetry in y. Again, we go through the same process now. The only difference now is that we're letting y equals minus y, and we go through the same procedure, only to find in this case, when we combine the integrals, that now we have is the integral from 0 to b. And again, the argument of the integration looks very much the same, except in this case it's y and minus y, whereas the case for symmetry in x, it was x and minus x. All right, so let's look then what happens if y is even or odd. We go through the same procedure as before. If this is equal to this, then these two are identical to each other, so it's equivalent to twice times f of xy. If they're odd, then these two subtract, the integrand is 0, and the result is 0. So here are 2 examples. So in this case, y is even. Why? Because this is y squared. No symmetry in x. On the other hand, in this case, we have y basically being an odd function and no symmetry in x. All right, now the case symmetry in x and y. And so here we now basically are saying that x equals minus x and y equals minus y. And so we basically make those substitutions in these expressions. In this case, basically, we've chosen to change the variables in the first and second integral, followed through, done all the calculations, and end up with the expression shown here. Notice now that this is xy, and this is minus x minus y. Now, we could have also performed a change of variables for the first and third integral on the right-hand side, in which case we would have a slightly different expression, but still, or nevertheless, this is x, this is minus x, this is y, and this is minus y. All right, so this is an example for a situation where we have x and y either even or x and y odd. So if you look at this expression, all right, this is an even function, right? Because f of xy is equal to f minus x minus y. You can see that for yourself. In this case, basically, we're dealing with the case where f of xy equals minus f minus x minus y. So in this case, we're dealing with an odd function. All right, then we look at the conditional symmetries. Again, starting with the fact that you've broken this up into 4 different sections. And all I've done here is basically go through the procedure of saying this condition is satisfied and this condition is satisfied, and then making use of the previous results. We can essentially show that this can be simplified down to an expression that ends up being just times 4 times the integral between 0b and 0a f of xy dxy. Right? So this more or less is symmetry both in x and y, and you end up basically with a situation. Again, it's a conditional. This condition is satisfied and this condition is satisfied. This is satisfied by virtue of the fact that both of these satisfied. With all of these satisfied, and we end up basically with this expression here. A second conditional statement is if fxy equals minus fxy, or fxy equals minus fx minus y, both case odd functions, then we end up with this final result. In both cases, the value is 0. All right, you can graph these for these particular conditions. You have even x and even x, even y and even x for this case. In this case, you have odd y or odd x. All right, and so these are examples, to illustrate conditional symmetries. So in this case, you can clearly see that for every quadrant, the results look the same. So integrating just over 1 quadrant multiplied by 4, this is equivalent to trying to integrate over all 4 quadrants. All right, in this case, basically it's odd in every respect. So when you do this integration, you'll find you'll end up with an answer of 0. This concludes Lecture 10C. Thank you for listening.